Good morning to everybody. In 2010, in the model code 2010, we introduced for the first time fiber-reinforced concrete that has a long history because it was born in the 60s. And we had also the opportunity to discuss in the Eurocode the basis introduced for the first time in the model code 2010. And this was a fantastic test bench to understand if all the main assumptions could be realistic or not. And I would like to use the time I have here, 15 minutes, to put in evidence three main concepts by means of an experimental investigation that was carried out with the help of a lot of people belonging to the framework of the Eurocode 2, because this was, in my opinion, very interesting, and it will be also considered in the new model code. We have essentially three concepts I would like to discuss. One is the minimum reinforcement in bending. You know that there is a minimum related to the capability to satisfy the cracking moment, at least, and another one which is able to control the crack. There is a problem of durability, which is strongly related to the crack distance, and also there is a general problem about the ductility of the structure in order to know if you can use limit analysis or not. Well, we started from this experimental campaign where we adopted a conventional reinforcement. You see the numbers. We had essentially two materials, one with a type of fiber which is a classical hooked fiber, and with the same geometry, you see, between the two type of fiber, and we used two different amount, 55 or 70, suggested by two important companies who participated to the discussion and are co-author of this, so Arcelor from one side and Becker from the other. And you see that the only difference is the amount of the superplasticizer between the two mix, and the shape are similar. The only point is here we used a double hook, and here there is a simple hook. So Arcelor is simple hook and Becker is a double hook. You see that the mix 55 means fiber content, A and B is a type of fiber, 70 is the other fiber content, and when you use plus R means that we are using that material but with reinforcement. And when we built this type of material, we did other tests. So the material is the same, but the bench was different. Well, in terms of the steel for the fibers, you see there is a difference between the so the Arcelor one was a little bit lower in terms of strength of the other one. When we did the first test, which are based on the classification, this is a very important point because we would like to classify the material by means of this test. You see that practically all the type of material are around 5D. There is only one that was able with 70 kilograms of fiber to become some 5E. And there was a situation that was interesting to know, because it happens sometimes, that with in one case, so the case where we have 55 B plus the reinforcement, so the bench where we use also the reinforcement, was only 2.5 E with the same amount of fibers, and 4A was a case where you have a 55 B. So this is the same material, you see, but two different benches. So one very important question that sometimes happen, are we able to guarantee always the same class? And the reply is very simple. Depending on the mix, you can see here the difference. You can change the standard deviation, And you can change a little bit the average value, which are correlated if you cut your specimen in 3 parts, also to the number of fibers that you have, of course, in the most important one. So this means that accordingly to this very simple equation based on this coefficient that was introduced by Lucie van de Waal and this group for this type of test, which correspond to the orientation factor, you find this number of fibers, 0.64 or 0.82. And you see that the number for square centimeter, of course. And if you see the numbers here and the number here, there is a very important difference, especially in the part C. So this means that if you don't put as the best your material, because we selected only to mix, we didn't optimize with respect to the fibers, you could have such kind of problem, which is very important to know that you can have. Well, if you put the fiber content versus the FR1 and the FR3, we always see that the fitting give us a hardening material, because the blue one, which corresponds to the FR3, is always larger than FR1. And the 2 lines correspond to the theoretical values that we could have in terms of fiber content. You see the 2 mix, which show different scattering in terms of fiber content. Well, when we analyze the behavior in terms of minimum reinforcement, Professor Danziger with this group in 2016 showed with experimental research that there is a problem with the minimum reinforcement. Why? Because fibers introduce an heterogeneity. And so if you have a large scatter, the risk is that the heterogeneity covers the ductility of the reinforcement effectively. So if the reinforcement ratio is only, for instance, 1.5 per mil, the global behavior without the fiber is this, with the fiber is this. And progressively, if you increase the reinforcement ratio, this phenomena, of course, fibers loses importance in the global bending, but you don't lose any ductility. And when you increase a lot the reinforcement, fibers give more. So this means that, of course, there is a very important point if you want to guarantee ductility. Well, when we investigated our shallow beams here, you see that in blue you find the intradox measure of the crack opening. You have essentially 6 measures on the bottom and 2 measures on the top. And we measure also the displacement in the load knife point and in the support. And we compare the classical reinforcement concrete solution with the solution where you have these 2 bars and you have also 55 A or B, of course. So when you put fibers, 55 kilogram per cubic meter, in this case, so 5D, we reduced the amount of reinforcement, and we investigated also the case when you added the largest amount with 70 and you don't have any type of reinforcement. So this is a classical idea of complementarity between the conventional reinforcement and fibers. If we look to the reinforcement ratio, we are close to 0.29%. And if you compute the minimum reinforcement for the cracking moment without considering the effect of the fiber, you have 0.25, so this is larger than this. And if you consider the minimum reinforcement for the crack control, you have, depending on the FR1M, 2 different values, which correspond to 0.2 or 0.5%, depending on this value. And we saw that there are different average value for these materials. Well, when we did it, you see what happens for the conventional reinforced concrete structures, and what happens if you have reinforcement plus 55 kilograms. This was the behavior, and here is the situation of 70. So if you have 70 kilograms, you couldn't guarantee always ductility, and sometimes you have, as in this case, one main crack, and you cannot have even a quite significant crack pattern. So obviously, the number of fiber we put inside is not enough in order to guarantee the same ductility of reinforced concrete structure. Well, we can conclude that in the model code, we cannot have never in a linear element fiber can substitute longitudinal reinforcement. Not only, when we want to guarantee ductility, we need to double the minimum reinforcement. So essentially, you have to use a crack control amount in order to have and to guarantee ductility. So this is the first point. Now let me pass to the crack distance. You know that according to the equilibrium, neglecting what happens in the two exterior part of this equilibrium, so we imagine to be in a tie, we have to consider this effect on the crack, and considering this effect on the crack, you have this contribution. And this means that you can reduce the crack distance. Sometimes we can also work on this subject because we know that tau BM could be increased, but at the moment there are no enough formulation to do it. So we like open the door to design by testing. So if you find a better behavior of tau BM, you have to check, and then you can introduce to evaluate this in this equation. What is very important that when you use this equation in shallow beams, you lose a contribution of equilibrium along the two parts which correspond to this perimetrical, or this, if you like, border surface. And what happens that essentially, according to the equation we have that we arrive to this expression with this assumption. And in the annex L now we have this equation always, or this one, you have to consider the minimum one of this. But if we consider the minimum, the risk is that you are using the equilibrium equation without considering the effect of the surface, the border surface. And in our opinion, it's much better to pass or to switch always to this one. And this is something that we are discussing. Anyway, if you look to the results, this is the experimental value that we had in terms of average crack distance. So we had some, of course, we have the possibility to count the global number of cracks in a certain zone, so we can compute the average the average crack distance. Okay, and here you see what happens with the AC2. So essentially, by imagining to switch the case of H main X from the equilibrium one, or when you consider the minimum global. So if we work with this minimum, we risk to be not on the safe side for this case. And we have also to remember that there are special cases where if you have reinforcement which is not homogeneously distributed in the cross-section, create situation where the crack distance change. So for instance, in this situation of you can have even 3 different crack distance, depending on the zone where you are, which is the reinforcement ratio in that zone. When we pass to the limit analysis, so to the global ductility of the structure, a lot of people ask if it's possible to put the reinforcement, for instance, in a square slab only on the perimeter. So this was one of the subjects we would like to investigate it. We put this type of longitudinal reinforcement on the perimeter. We measure all the crack opening in the zone close to the corner and in the center where we put the central load, or at a certain distance, so essentially in the average, always on the bottom. And we compare the situation with the case of 55 plus or without reinforcement, and 70 without any type of reinforcement. What happens? We had 2 different labs, because as you've seen at the beginning, this was done with the cooperation of the University of Bergamo and the Prizzari team. We had essentially 2 different supports, and there is a different stiffness between these 2 supports. The results we obtain is this. This is the 2 lab, L1, L2, and this is what happens when you have 55 only, Arcel and Becker in this case, 70, or the case with hybrid, so when you have also reinforcement. So even if you don't have a distributed reinforcement but only as a perimeter, this is enough in order to guarantee a better ductility. This is obvious. But you see also the design and the average value, which are always the design one on the safe side. We analyzed also the crack pattern. If we put this lab without choosing a special way to mix, so not only, for instance, casting from the center, but casting in a not exactly random but quasi-random situation, you find that the fiber could be distributed in different way, and not always you find a full cracking pattern, which is what we assumed in a limit analysis. But and this is the case, for instance, for the two lab. It's very interesting to know that the crack pattern evolves in one direction and then in the other one when you reach a certain load. That means that even if you don't have exactly a crack pattern, you have a stress which is very close to the value that you have in mind. And if we compare the ductility, we reference to the cracking value, we reference to the and the peak one, or in terms of displacement, evaluated when the load is only 85% the maximum peak load, and the cracking one, you find the ductility values that we obtain in all the situation. So the ductility is enough to use limit analysis, and if you are a designer, usually you don't take into account this possible contribution close to the support. You work with this, and so you compare this design value and this average with the minimum experimental value we obtained, and you have always a factor which is at least 2. That's all. Thank you for your attention.